You know, from the mud settling in a river all the way to the medicine you take, there's this kind of hidden rule that controls how tiny particles move through liquids. Today, we're going to pull back the curtain on that rule. Stokes Law.
I mean, think about it for a second. You shake up a bottle of, say, salad dressing, and you watch all the spices and herbs just slowly drift back down to the bottom. What's actually controlling that speed? Why don't they just drop instantly? Well, the answer is all wrapped up in the physics of suspensions.
And yeah, there's a name for that whole process. It's called Stokes Law. It's the scientific principle that basically gives us the exact rulebook for how quickly particles are going to settle in a liquid. It's the why behind what we just asked.
Okay, so let's dive in and really decode what Stokes Law is all about. You can think of it as the official guide, the rulebook for settling.
And what's really cool is that this whole thing, which seems pretty complex, right? It all just boils down to 3 key factors. If you get these 3 things, you've pretty much mastered the entire principle.
So what are they? First up, we've got particle size. Makes sense. Then there's the density difference. Basically, is the particle heavier or lighter than the liquid it's floating in? That difference is what gives gravity something to work with. And finally, liquid viscosity, which is just a fancy way of saying how thick or thin the liquid is. That thickness creates drag.
Now, science loves to put big ideas into these neat little packages, and this is it, the formula for Stokes' Law. And I know, it might look a little intimidating with all those letters and symbols, but don't worry, it's literally just a math sentence describing the 3 things we just talked about. We're about to make this crystal clear.
Because you really don't need to be a math whiz to get this. That whole complicated formula, it can actually be broken down into 2 super simple, really powerful rules.
That's right. All that math. It just gives us 2 key things to remember. Let's get to the first one.
So rule number 1 is all about the size of the particle. And the rule is dead simple. Larger particles settle faster, smaller particles settle slower. Just picture dropping a huge boulder into a lake versus a tiny little pebble. That boulder is going to sink almost instantly, right? But the pebble, it takes its time. It's the exact same idea here.
All right, rule number 2 is all about the liquid itself. Its viscosity, or its thickness. In a thicker liquid, particles settle way slower, but in a thinner liquid, they settle much faster. Think about trying to drop that same pebble into a jar of thick honey versus a glass of water. It's going to slowly drift down through the honey, but it'll zip right to the bottom of the water glass.
Okay, so we've got these 2 simple rules. Bigger particles sink faster, thicker liquids slow things down. But why does any of this matter? Well, let's look at a really critical real-world example, pharmaceuticals. This is where Stokes' Law isn't just a cool theory. It's absolutely essential.
So here's the challenge that pharmacists deal with. In a lot of liquid medicines, what we call suspensions, the actual drug is made of tiny solid particles that are just floating in a liquid. The number 1 goal is to make sure those particles stay evenly spread out so that every single spoonful, every single dose is effective and, safe. You can't have all the medicine just sitting at the bottom of the bottle.
So, how do they solve this puzzle? You guessed it. They use Stokes' Law. It's this brilliant 2-step solution. First, they use rule number 1. They make the drug particles incredibly tiny so they settle much slower. Then, they bring in rule number 2. They make the liquid thicker. They increase its viscosity to slow that settling process down even more.
And what's the result? By perfectly controlling the particle size and the liquid's thickness, pharmacists create a stable suspension. This is what makes sure every single dose is safe and does what it's supposed to do, from the very first drop to the last. It's a perfect example of physics solving a major healthcare problem. And really, that's the bottom line here. For anyone out there studying pharmaceutics, this isn't just some random concept. It's absolutely crucial knowledge. As our source material points out, this concept is very important in pharmaceutics and Gpat exams. It's the science that keeps our medicine working right. And it's definitely something to think about the next time you see a bottle that says, "Shake well before use."